So first of all, whenever I was doing my slides earlier, someone asked me why I had Boris Johnson on my opening slide. I just want to clarify, that's not Boris Johnson, that's actually David Attenborough, who is one of the premier living conservationists and opened the building that I work at, which is the David Attenborough building at the University of Cambridge. And this work I'm going to talk about has been in collaboration with lots of computer scientists, but also with ecologists, zoologists, and conservation practitioners as well. So I've listed some of their names on the slide here as well. And to just give you a contextual idea of where I'm coming from, the problem that we're facing right now is that all of the world's land is more or less used up. So it's either used by humans for anthropogenic reasons, so productive agriculture, industry, that kind of thing, or it's being used by wildlife for the furtherance of biodiversity. So that is just any life that isn't humans on the planet right now. And the problem is that all of the uses of anthropogenic land are causing lots and lots of interconnected damage across the world. So it's not just one thing, it's lots of things all being put together. So the first thing that we've all heard of are greenhouse gas emissions from general human industry. And emissions have been rising steadily. They still haven't quite peaked yet, but we're hoping for humanity's sake that they have peaked sufficiently that we can start to arrest the common resource that is the atmosphere and the greenhouse gas effect that it has as quickly as we can. But then, in addition to just us causing carbon emissions, there's also a huge crisis in terms of our impact on other living things on the planet. So, in general, the number of regularly counted terrestrial species have declined by a huge amount since the 1970s. So I think it's 69% on average for regularly counted species. And in some parts of the world, such as the Amazon, it's over 90%. So our general use of land has caused lots and lots of things that would otherwise be thriving to also fall apart. And then we also have this problem of making sure that these ecosystems can continue to supply the services that we need for human existence. So for example, water is a big driver for everything that we do, and this destruction of natural ecosystems has also put the water system under stress, and so lots and lots of the global south will have trouble with making sure that it has enough water to supply human needs, let alone wildlife needs in the next few decades. And so ultimately, this is all pointing to a big, interconnected, complicated data structure where changing one thing has an opportunity cost on something else. And so we really have to start figuring out how we can start to quantify this opportunity cost so that we can make sensible decisions that aren't perfect, but are minimizing harm elsewhere in our ecosystem. And the good news is that we actually have a lot of agency to fix this problem. So we've seen all of these doom portents happening, but the reality is that we actually know more about our planet than we ever have in human history. So satellites are giving us lots and lots of data. The problem is going from that source to something that we can action for a policymaker, a politician trying to decide, for example, some agricultural policy, is really, really difficult. And the thing I'm going to talk about in this talk is how we could start to connect the dots computationally from this source torrent of data that's going all over the globe to where we are right now. And the good news is that we do understand how we could take complex, interconnected data structures and put them together into a more cohesive whole. And there are superhumans that can come and save us, and these are functional programmers. And so what I'm going to try to give to you in this talk is, first of all, an empathy for the problem domain. So I'm going to describe some of the natural ecosystem problems I've been looking at over the last few years. And then we'll talk about how we're applying functional programming in order to make it more tractable and feasible to solve it. And then there's lots and lots of work to do. So I'll lay out some of the landscape that will hopefully get some of you here involved in functional programming for the planet. So to begin, you first of all got to figure out where do we start tackling this enormous problem. And one of the most interesting areas on the planet is just about 4% of the world's land surface, the tropical rainforests. Who here has been to a tropical rainforest in the equatorial belt? So I say about 1 in 6 of you, I estimate. For the rest of you, it's an incredible experience to go there. It's kind of a once-in-a-lifetime experience, well, unless you go there twice. And what it shows you is that there is a huge three-dimensional amount of life that packs in many, many more variety of species than anywhere else in the globe. And the reason for that is because it has the perfect conditions to breed life. It's warm all year round, it's got lots of rain, hence the name rainforests, and it's got lots and lots of the essential nutrients required to kind of pull that off. But the problem is that human uses of rainforests have causing decimation of the amount of land that is covered by tropical rainforests over the decades. So this is Ecuador, and it's showing that in the 1970s it was mainly covered by forests, and then lots and lots of logging for various reasons, such as agricultural, which is about 95% of the use cases for this. And then by 2010, you can see that most of the island has been decimated. And so there's been a knock-on massive effect on biodiversity. And ultimately, if we want to save 2/3 of the world's terrestrial biodiversity, we have to save just 5 major rainforests around the world, which represent a minuscule percentage of the land surface. So this is Colombia, the Amazon rainforest, the Congo region in Africa, Madagascar, where 90% of the world's vanilla is produced, hence deforestation, and also the Indonesian regions as well, the Eastern Ghats. So it's not a huge amount of the world's surface, but there's a lot of really, really good reasons to protect that against any anthropogenic use. And so the problem is, of course, that this equatorial region is also some of the world's poorest countries for various reasons, for colonial reasons, but just generally speaking, that they need to have a path to prosperity that will make them as rich as we have become in the West by benefiting from the industrial revolutions that have powered our growth in the last century. And so we're looking for alternative livelihoods that will provide a way to make lots of good money for the locals, but also maintain the integrity of the rainforests and provide financing to supply any differences so that they don't cut down the rainforest, for example, for palm oil. And one example of this is in the Gola rainforest in Sierra Leone, so a country that was racked by civil war until about a decade ago. And instead of the palm oil manufacturers coming in and cutting down the rainforests, one of the projects that we've been working on is sustainable cocoa production. And so if you say that we can have a lower yield of cocoa inside a rainforest, then there's lots and lots of benefits where the rainforests are old-growth forests. They save lots and lots of carbon. They're the lungs of the earth. It improves livelihoods because they can not only curate the forest, they can also create a coffee trade, a cocoa trade. It preserves biodiversity in this area because it's a rainforest, it's very, very dense, and it also protects the world's water systems as well. So it's generally a win-win if we can craft these alternative livelihoods and make sure that they are viable financially to the local people. But the problem is, we're in a situation a little bit like the medical industry was before we learned how to do controlled, randomized controlled trials, where we need to figure out how to assess if an intervention is actually effective against a counterfactual which is unpredictable, because we don't know and we can't predict which way the world is going. And so what we're trying to do is to assess whether or not a protection project is better than doing nothing at all, and if it is better, how much better is it? And the problem right now with assessing these projects is that every single one of these conservation projects self-declares a baseline, and then it measures itself against its own baseline. So this is a bit like me giving an aspirin to all of you and just saying, just let me know how you feel before you take the aspirin, and then let me know how you feel afterwards, and then deciding how effective aspirin is. Clearly, we need a more objective mechanism of randomizing these trials and just generally assessing it more objectively in a way that is comparable without relying on self-reporting. And so this is where we started getting into using satellite data in order to figure out if we can create a global data structure that would describe the health of all of the rainforests worldwide, and then use that to measure different interventions and try to put them all on a common playing field. So the good news is that the data coming into this, obviously when you start a computation, first thing you want to do is determine exactly where the data is coming from. And there's over 10,000 satellites, eyes in the sky, of which roughly 10% are dedicated for the purpose of Earth observation. And what these do is that they sweep over the planet and they have lots and lots of different orbits. So this is the NASA Landsat going on a north-south orbit. Other ones go east to west, depending on exactly how they're deployed. And they deploy different types of instruments that measure some aspect of the Earth. So the most common ones are multispectral satellites that take near visual or visual pictures of the Earth. There's others such as radars, synthetic aperture radar, and hyperspectral. And what they do is that they go round and round the Earth, and then eventually we have to stitch together the images, removing things like clouds, for example, into the more familiar maps that you've seen before. And once you're done with this, what we do with these multispectral images that we stitch together is that we measure the reflectance of the signals coming down to the satellite. And then the reflectance pattern tells us what is actually below us. So in this case, if you look at the wavelength of a particular signal sent down to Earth, the visual range is 0.4 to 0.7 micrometers. But you can see that just outside the visual range, we can detect grass and soil and water really quite accurately. And then if we zoom in a little bit more with higher resolution instruments, we can even detect the different types of trees that are reflecting back and start to segment with a pretty good range of accuracy what we're actually seeing on the planet from space. But this gives us some coarse-grained maps. So this is a map I pulled together of Brazilian deforestation in the Amazon, and you can see that since about the 1990s, the orange map represents degraded forest, which is forest that has been significantly cut down so that the primary forest is now secondary forest, and you can start to now build a map of exactly what the world looks like. And this isn't quite enough, though, because this is telling us where the deforestation is. So in order to get a really accurate view of the world, we then decided to use a giant space laser. And there is, in fact, a giant LiDAR, so a big laser of the kind of you would use in a self-driving car, on the International Space Station. And this instrument is so accurate that if you look at the raw data, we can actually detect when astronauts on the ISS are going to the toilet because they're flushing. And so it is tracking in real time across the planet a laser array that measures the reflectances coming back up, and the return delay as a spread of a signal tells us about the height of the Earth and also the shape of the surface that we're looking at. So earlier, we were using visual wavelengths or near visual to figure out what was there, and now we can also measure the height of the planet as well. So the combination of these instruments is now letting us put together a combined kind of multimodal view of the world that tells us not only what we're seeing, but it's starting to help us infer what it is down there as well, and also how high it is, and you can start to come up with some really beautiful three-dimensional views of the whole planet, using only satellite data to start with. But then, let's go back to our original problem, which is that we've got this 4% of the world's land surface, and we're trying to figure out exactly how deforested that is. And so, if you start putting this into a computational framework, what is the algorithm that we're trying to solve for? So we're trying to, given time, we're trying to measure the amount of forest that's remaining, the net carbon stock, and we're trying to figure out, first of all, how additional was the intervention. So we're trying to predict the future with how the world would go without an intervention, and then if we do have an intervention, we can then figure out how additional it is by looking at the difference between what would have happened and what did actually happen in the past. So how might we do this? And so let me show you one example of this. So if we're in Sierra Leone here, and then I could zoom into the Sierra Leone area. Let me just refresh this so we're here. And so this is just off the west coast of Africa. And we're going to try to treat this like one of those drug trials I described. What we're going to do is we're going to sample some areas within the forest, and then we're going to say, well, can you show me where there are areas outside of the protection area that are as physically similar as possible to this area I've just found, but the only difference being that one of them is in a conservation area and one of them is normal. And so we look all over the countryside in Sierra Leone, and we find ones that have the same parameters based on our satellite description, so the same elevation, the same slopes, because different types of trees grow in mountains, the same accessibility to roads, which tells you can't really log a forest unless you have a road there to take the logs away, and also just how long have they been disturbed for and how long have they been undisturbed for. And then what this lets us do is to build an analysis that says, well, if we look at this over the last 10 years, this is live data, then we can see that this is how much the area that is being conserved is protecting its forests, and this is how much the area outside, that is our control area, is also not losing its forest. And then you can see here that the difference between the two, so recall that we have the green is our conservation area, and the blue are our control points. And so we can measure the difference and therefore come up with some notion of additionality. So this obviously required lots and lots of number crunching, but you could see how we could go from satellite data, and then we could start doing all this pixel matching and searching in order to figure out, based on a purely computational mechanism, how effective a particular region of the world is at protecting its forests versus other physically similar areas of the world. Unfortunately, this isn't quite enough in the real world, because we have one huge problem called leakage. Now, imagine that we are proud protectors of the Sierra Leone rainforest, but we've actually stopped growing palm oil in this particular region. Now, the demand for palm oil is not decreasing. And so by reducing the productivity of one bit of land, we've just shifted the problem elsewhere. We've just said, well, you might be deforesting just next door to the conservation area and continuing to grow your palm oil while also getting the money for growing this cocoa. Or the demand is shifted somewhere else in the world and somewhere else is being deforested. Fundamentally, the only way to reduce deforestation worldwide is by reducing demand or by increasing the intensity of agriculture. And so we're trying to also detect whether or not our project is causing some unintended harm somewhere else in the world. And it turns out that you can start to reuse some of the same algorithms that we've designed previously, except deployed with different parameters. And so instead of looking for these matching pixels right on the same, within the same country, we can say, well, look for them within a buffer area around the project itself, and just try to see if there was an increased deforestation just outside the project area. So this way, if you're just shifting your deforestation locally, you can detect that. But it is like trying to find a needle in a haystack. You need lots and lots of precision. So this example here shows you those tiny little polygons are the actual forest areas that are being protected, and then all of the degraded areas are just beside it. The green show where there's been positive growth of trees, and the red shows where there's been deforestation events. So this algorithm requires lots and lots of precision. But ultimately, at the end of all of this, I just wanted to give you a sense of some of the algorithms involved. We can end up with what looks like a computer science algorithm. So we can say that, well, if we're going to measure forest health assessment for tropical forests, well, we need to measure the additionality of the intervention. We need to subtract any negative damage caused elsewhere in the world. And then we need to also adjust across time for the fact that it might not be a permanent sequestration of carbon. And then you can come up with an equation that kind of makes sense. So the question is, how do we go from this to something that can actually be usable by the world's policymakers? And bear in mind that this is just one algorithm that we're looking at, and there's lots and lots of other problems in land use that we also want to apply this to. And this one algorithm took us 2 years to implement, along with all of the dependent libraries and so on. And so we want to do this in 2 weeks. And how do we speed ourselves up? Well, the thesis behind planetary computing is that we need an entirely new set of global infrastructure to handle the lifetime of this planetary information in order to accelerate environmental science and policymaking immediately. But we can't just do it as a public service. We also need to handle security, because lots of the data involved is politically sensitive or might do harm in the hands of bad actors. And so we need to figure out how to program these things with many of the technologies you've seen in today's and yesterday's Lambda Days talk. So things like information flow control, as a previous speaker talked about, and also other kind of non-interference properties. And so when you put this into a pipeline, the pipeline is actually pretty straightforward. You have to ingest exabytes of data from decades worth of satellites, and there's over 10,000 satellites, so it's lots of data. And then you need to figure out how to transform them into a form that you can run algorithms over. You then need to analyze them, iterate as new data comes in, and then ultimately publish the results in such a way that it can survive the test of time for decades, so that it can be used as a basis for policies that will affect the lives of billions of people. And the good news is that this is very much a functional pipeline, right? We should be able to use all of the good things we've learned from functional programming over the decades in order to implement what is ultimately an immutable data structure with lots of data. So the numbers are higher, but the essence of it, the heart of the implementation, is ultimately a purely functional pipeline that just happens to scale worldwide. And it turns out that when we started working with the scientists, that this discipline actually worked out really well. The first thing that we did was just go and hang out with the actual practitioners. So I moved my office in Cambridge from the computer science department to the conservation initiative. And when you begin to work with the people who are actually doing the computational work, what they're doing is really ad hoc and manual. So they're writing some R scripts, they're curling something from the web, they're uploading it to a cloud service, and then eventually they get the results back after lots of out-of-memory errors. And everything is just all over the place, and they just give you the results, and you can't reproduce that information. This is a typical scientific computing workflow pipeline, which I myself have done many times while getting to grips with it. But instead, so we worked with them to say, well, why don't we start restructuring this into a more consistent pipeline? So one which says that we should first of all consider what our inputs are. So for example, the satellite data that I showed you earlier. And then look at what some of the intermediate analysis algorithms are. So one of them was the additionality one, which does the matching of the pixels and so on. And then ultimately, we have some result, for example, the estimation of carbon worldwide, which should come out of this pipeline. So this is pretty straightforward for the kind of things that we do in functional programming. When it comes to structuring these pipelines, we have lots and lots of building blocks that tell us how to do this in a disciplined and a mathematically rigorous way using, for example, concepts from FP such as monads and applicatives. So that's what we did first. I'm an OCaml programmer and maintainer, so we decided to build this data flow system in OCaml. And a lot of these things should be familiar to you even if you're not an OCaml programmer. So the idea is that we wanted to sequence together lots and lots of different terms, which are individual nodes of computation. And then each term has a basic description, so you can render a user interface for it. And it looks like an applicative. So you can say that we can map over a particular term. And it's applicative because there's no T here in this beta, so it can't depend on its input. And then you can have some useful combinators. In the real interface, there's lots more. And ultimately, you want to join it together into one computation. So the power of this is a static data flow graph. That is, it cannot have computations that vary based on the input data, because it's purely applicative. And this is really good when you're rendering user interfaces because you want to see exactly what the shape of the computation looks like. And it's generally more predictable. But then you can then add in a little bit of syntax. So in OCaml, we can override the syntax of let operators. So you can just say that instead of all these maps and pairs, let's use our familiar let bindings to make that work. And then we also added in more powerful dynamic data flow, so via monadic bind. And what this lets you do is to say that, well, given a node, if you can't predict a priori exactly what it's going to do afterwards, then the bind operation will let me effectively spawn dynamic data flow on the basis of what the computation did. And although it's less predictable up front, it's much more powerful from an expressivity perspective. And we also then augment the DSL with, for example, metadata, so you can render the pipeline and build a cool user interface out of it. And then all we had to do was actually pretty simple. We took all of the little Python fragments that the scientists came up with, lots of R, lots of Python, sometimes some web services that were harder to wrap, but ultimately, we just wrapped and hoped that they were vaguely deterministic. And then you could write some OCaml code that would use this DSL in order to run a sequence of containers using Docker that were isolated enough for our purposes such that we could reasonably reproduce the results. And this example here is just defining one node saying, go run this Python script with this particular input data and give it a cookie file so that it can reproduce some randomness and then ultimately put the output in a particular part of the file system. And then the actual pipeline is just a normal OCaml program. So the tropical moist forest one I just showed you, it fetches the AGB bounds, the above ground biomass estimations from the satellites. It finds the matching pairs of points in the map that were all those little arcs that you saw. And then it calculates additionality through a series of complex algorithms and leakage impermanence, and then it ultimately does the computation to return the result that you're looking for. So it is possible to take one of these quite complex calculations and express it in this functional style. And there's lots of really good properties for these DSLs. So the first thing is that we force the computation to be more structured. We're not telling the programmers on the other side to rewrite their code. We're building what is effectively a fancy continuous integration system that says that we want to just know what your intended inputs and outputs are. And so we do all the accountable programming, and we provide them with a nice little pipeline. It's also scalable because the interpretation of this DSL can easily just move across thousands of cores because of the huge amount of data involved. And then it's also explainable. So if you got one hint from Phil Wadler's talk earlier, it is that you don't want to just casually introduce machine learning into your pipeline. And what's happening in the Earth observation space is that everyone is essentially just deploying machine learning willy-nilly. And what we're trying to do is to structure our code in such a way that we can use machine learning, but contain it within a module such that we know when the results of something are themselves machine learned. And if we do get new original data, for example, from new observations, we can either retrain the pipeline, but we'll always know what were primary observations and what are inferred observations from these pipelines. So it's extremely important when you're dealing with policy to be able to explain the results. And so these kind of approaches that we're taking, we feel, should surround and wrap any machine learning so that we can always keep track of where things are. So this was really good, and it taught us about how to use monadic data flow and generally structure our transformations. But one amazing thing happened when we started doing this. And that is that we're getting all these complicated graphs, but then scientists were going off and looking at the intermediate results. And so they all said, well, look, this is really nice that you've solved one problem, but we have 100 other problems we need to solve. And so what they wanted to do was to start looking at the internals of this pipeline. And so what we did was started building a user interface where you can look at one of the pipeline jobs. And when you look at one of the pipeline jobs, you can look at what each individual thing is going on there. So you can see this is the Docker container with all the low-level apt-gets and so on that put up the interface. But you can also then start inspecting the edges. So you can say that, for example, this particular job is looking at some aspect of additionality calculations in Indonesia, and it's got these particular inputs with this particular hash, and you can essentially debug it and kind of figure out what's going on. And then you can see the progress of the pipeline, but you can also see the progress of all of the other pipelines that are running, and then decide exactly where you're going to go and navigate the entire interpretation of the DSL across lots and lots of different things. So this was useful, and it helped us to kind of figure out what the results were, but also what the interesting intermediate results were. And this then allowed scientists to come along and say, well, okay, we're going to now use this to calculate something entirely new. So they went from carbon estimation to trying to figure out if we could build a global map of the world's biodiversity, which doesn't really exist at the moment because of the huge amounts of data that you have to work your way through. And so this metric called life has been a joy to work on for the last few years, because we were not only catching up with the science, we're now contributing to advancing the global state of the art in our understanding of the world. And to give you a sense of scale about this particular metric, the life metric, what it does is it calculates the probability of extinction of every single species that we track. So around 45,000 terrestrial species, not aquatic ones just yet. And what it does is measures the probability of persistence against the proportion of habitat remaining. So it should be fairly obvious that if I have 100% of my natural habitat remaining, I have a certain probability of extinction. In the long term, it's 1, but in a certain time period, it's bounded. And then as my habitat disappears, we should be able to calculate the curve that tells us what my chances of extinction are. And this is a nonlinear curve. So it doesn't just smoothly drop off as my forest disappears. At some point, there's a tipping point, and most species just give up around kind of halfway in. And it varies per species, and often there's lots of codependencies on these curves. And so we started calculating this across all of the knowledge we could find, and working with the UN to pull together each individual set of species observations and see if we can come up with a global map. So the first thing, to give you an example, is the nearest living relative to the elephant in Africa, the bush hyrax, very cute, it's about this big. And you can see from the IUCN website, these are the ones who keep track of the extinction lists, where it exists in this part of Africa. And so our processing pipeline now says, well, let's figure out the ranges where this particular animal lives. Let's figure out its natural elevation. So we use the three-dimensional maps of the world I showed you earlier to basically highlight the fact that the bush hyrax doesn't live high up, it only lives at lower altitudes. And generally what its habitat preference is. It doesn't live in the middle of a lake, it usually lives on land. And then you can use this to combine into an area of habitat that for that one species tells you exactly where it could live. And we do this for 40,000 species with lots and lots of large images. And so the amount of data involved is petabytes and petabytes of data. So you can see how having this structured pipeline was really useful, because even though the algorithm is pretty simple for one species, we just suddenly want to multiply this by 40,000 and maintain the ability to have overrides inside each one of those things. So to give you a sense of, this is a computational pipeline and what it looked like, I think it's always worth having a quick look at the map itself. So this is a false color version of that map, which shows you red for mammals, blue for birds, yellow for reptiles, and green for amphibians. And if you zoom into some of these areas, you can see just how rich the global south is in terms of endemic species are black. So this is where if you destroy that bit of land, everything will disappear. So the birds, mammals, reptiles, and amphibians. And then other areas are more mammals and bird heavy, so the purple areas. And then as you get to drier regions of the world, lots of reptiles exist in there, along with lots of rare plants. And then some areas like Madagascar, where about 90% of the world's vanilla come from, is largely deforested except the eastern part, the wetter part of Madagascar. And so, but the rainforest remaining there is extremely endemic. And when you move up to India and Australia, the northern parts of Australia and the eastern Ghats in India, you can see there's lots of beautiful biodiversity there as well. But when you come up to my home of Ireland, unfortunately, you can barely spot it, and it shows you the magnitude of difference for biodiversity for flipping one bit of land in the tropics versus making one bit of land in this part of the world productive as well. So this continued, and this network effect has been growing almost beyond our control. So now another group has come along and said, well, let's figure out, if you have this biodiversity metric, how do we go from satellites to telling policymakers how to handle food imports and exports? And so you can build on top of this to say, well, if I want to calculate based on where I get my food from importing and exporting using the world's supply chains, this is supplied by the Stockholm Environmental Institute, the TRACE project, you can actually figure out that, well, the USA and Brazil and Uganda and India, well, Brazil and the USA eat lots of ruminant meat, so lots of beef and lots of lamb and goat, but they mainly produce it on their own land. And so while there's lots of biodiversity impact there, it's their local domestic decision. But then, if you adjust it for imported food, you find the UK and Japan are actually doing really bad things on a global scale because they have the same kind of levels of demand, but they import the food and cause deforestation in other countries. And so just casting the data and adding in some new data sources such as supply chains lets us build a view that is highly relevant to policymaking and in fact is informing, we hope now, lots and lots of subsidy policies in different parts of the world differently because of this angle. But of course, we can always go back through our data flow graph and justify where every single one of these graphs comes from because we have the source data behind it as well. And so this extensibility has been really fun because it's really shown how if you build an extensible system and you solve a problem, that the practitioners will work with you in order to pull that off. But it has been highlighting a huge problem, which is we are keeping track of all of this source code now, but the data inputs that are coming in are constantly changing. And this is causing real problems in how we create policy for the world. So the first thing, how many people here use Nix, for example? A few use Nix, so we're in Lambda days, this is great. I say about one in 5 of you use Nix. The problem is that if you modify even one of the libraries that are commonplace used for geospatial processing, you change the actual results. So this is a minor version upgrade of GDAL, which is the big geographical data processing library written in C. And it caused, the black and white graph shows the difference between the previous minor version and the new minor version. And it just gives you different results. So the first obvious thing is we have to keep track of all of the individual versions of software throughout this very complicated stack. But that's solvable, right? We can use things like Nix in order to keep track of all the different versions. The bigger problem is that science operates over decades. And so what's happening now is that different groups in the world are building different elements of this particular computation graph. Even if it's not formalized in this graph, they're doing different chunks of the problem, and they're using different data versions when they publish their results. And so it could be the case that if we depend on a forest model from 2013, that even the historical interpretation of what it means to be the world's forest cover in 2013 is different when you use different data sources to calculate that. Because our ability to process satellite data is also advancing every single year. So if, for example, we were looking at forest cover in Indonesia, let's say we care about what the forest cover in Indonesia in 2018 was. It turns out that if you zoom into this particular region, and you download from from the EU, in this case the JRC, the same data sets for in this case 2020, what we're showing here is a difference between the calculation as calculated in 2022 and 2023. So within the course of a year, there's been an enormous difference, roughly the size of I think that was Portugal, in terms of the amount of forest that was previously thought to be deforested and is now forested. And so we have to figure out, when we're looking at these global data sets, how to reconcile the fact that some computations that happened a decade ago must now also be recomputed, and to visualize the differences as well. Because if we don't do that, then we end up silently just making incorrect assumptions about past results, and because it's so expensive to recompute them, we simply end up with wrong results as well. And so this versioning of input data sets is actually one of the key problems that we're looking to address with planetary computing, and also realize the fact that if a data set has been released recently, then the people that are most motivated to use it are actually the bad guys. So if, for example, I get the latest data on deforestation from satellites, and I'm actually a company that is doing deforesting, I am economically more motivated to use that data than anyone else. And so we're seeing evidence that, in fact, having fully open data is quite harmful, but having data that is eventually open and only selectively made available to, for example, governments is a better idea than making them fully open. So we have to deal with data versioning as a systematic solution for all this. And of course, the solutions from functional programming are actually pretty straightforward, because if you have a computation pipeline that is well-defined and pure at its heart, then whenever we ingest the data, we just make sure that we do not randomly allow for mutation, and we then propagate through all of the differences as we go through. So this is actually relatively easily solved once we move things into a functional kind of framework. So the overall message here is that it should be possible to deal with petabytes of data at scale, and also still be quite efficient, but also maintain your principles. So we've got these DSLs and all these nice bits of functional technology that have actually solved many of the problems that we faced in the beginning when we started looking at this problem domain. And ultimately, we want to wrap this up in such a way that it should be really easy for any scientist to just use this and never have to know what a Lambda term is in their life. They should be able to use the benefits of functional programming to compose their workflows together, to collaborate with their colleagues, yet be able to drop down into kind of an advanced mode if they need to as well. And so ideally, functional programming is best hidden sometimes so that not everyone has to know it, but our systems should be built using it. And this is where we've run into some rough edges. So I wanted to spend the last bit of the talk just explaining to you some of the challenges that we're facing, and I think some of the hopes and dreams that we have about how we might be able to tap into the FP community to help us to solve them and to make the next iteration of the system really, really scalable and usable. The first problem that we have is that no one tech company can own the world's data. So no matter if you're Google or Microsoft or Facebook or whatever they're called now, it is the truth that the data gathering for these systems involves tens of thousands of local countries, lots of NGOs and governmental organizations and commercial entities there, hundreds of thousands of people working on each project, and policymakers that are depending on the results. So by its very nature, these things should not be a single system deployed by one organization, but a global federation of them as well. And so one of the things we're trying to figure out is, if we can build these nice functional fragments of computation and data, which has been gathered and snapshotted, can we turn this into a Wikipedia, kind of a planetary system that where anyone can zoom in on their area of interest, write a little bit of code, deal with the security policies to make sure that they have access to the local data, and then essentially avoid value capture by any one provider as well. And so it should be possible to build a usable thing, as usable as Wikipedia is, but with the safety net of functional programming, so that we can't have ill-typed computations wasting lots and lots of our compute resource. And one of the first problems we saw was that our users are actually experts in their field, but they're not experts in programming. And so a really nice paper in, I think it was ICSIA a few years ago, shows that a term for this is called vernacular programmers. They're really good at twisting Python to solve their problem, but it might cause a functional program to look away with a look of disgust. But these are exactly the kind of typical scientists that we want to use and find joy from using our systems. And so it turns out that DSLs were actually a really bad idea. So I love our little OCaml DSL. It's very nice, but no one else was able to successfully use it. And the list of problems when you give it to someone else is huge. The DSLs are typically a leaky abstraction. So the host language ripples up, you get type errors and all kinds of things, and it's also typically quite inflexible because you can't just leave a hole inside some computation and then expect it to be evaluated afterwards. It should be possible for us to continue fixing this DSL and make it good, but the other approach that we're starting to take is just follow what our users are doing. And what they love doing is running Jupyter notebooks. And so we've actually turned our DSL into Markdown and just told them, just write down what you're trying to say and just give me a few scripts with command lines that describe your algorithm. And then from there, we write an interpreter that interprets the Markdown and the natural text and just figures out what all the inputs and outputs are, and we can actually come up with a graph that represents our DSL. So we're staging Markdown, turning it into this OCaml DSL, and then doing all of the interpretation in the global DSL. But the beautiful thing is that when the programmer is editing their Markdown, they have a Jupyter-like experience, except it shows them what all the inputs and outputs are as they're doing it. So again, we're trying to follow the lines of what people find usable, but then always compile it to our DSL so that we have a really good, well-structured foundation for global execution. And so if anyone's interested, this little shell is called Shark, so SH-ARC. And it's an ARC for all the world species. And everything in Shark is written in Markdown, except for in terms of its documentation. And we're bootstrapping this towards becoming a scientific computing shell for this. But one of the big problems that is yet unsolved is the security model. And this is really, really vital to get right. Because a lot of the data that we're handling is, if it's ever leaked publicly, will result in the slaughter of tens of thousands of species. So to give you a slightly mind-blowing statistic, we have around 300,000 known species of plants worldwide, of which about 150,000 of those have had less than 5 sightings in their history. So the majority of species that we know about are actually data deficient. And if knowledge about where this species is leaked, then it will result in that tree being chopped down for rare furniture within days. And the same is also true for rare birds, for rare mammals. If you leak their exact location, then we're out of luck. And so what we have to figure out is, how do we build into these DSLs a notion of statistical robustness so that we never leak any individual data sighting, but we can still build global statistics about what is happening around the planet. And then if you have access and you've been shown that you're a reliable source of processing the raw data, that you can get access, but otherwise you can't. And we've seen lots of talks on information flow control of non-interference properties, and so it should be possible in this pipeline to label every single observation with a diffC label, and then figure out whether or not it's safe to declassify based on statistic tests. And so this is where decentralized information flow control is one of the key areas that we're looking at to make sure that we can actually keep track of where all of these different pieces are. And then, if we can combine this with memoization, we could actually then have incremental real-time recomputations while maintaining the privacy of the underlying raw data sets. So this is a holy grail in many areas of computation, but in terms of use case, this is one of the most compelling use cases where we have to have this before you deploy a global model. So if anyone's interested in DIFSIA, I'm all ears in how to express this in languages that are usable by vernacular programmers. And then, the other aspect of this is that the internet is younger than many of the projects for conservation that we're dealing with. So Cambridge has just committed to an afforestation regeneration project in the UK. It's committed to it for 120 years, because that's roughly how long it takes for a forest to go from a new plantation to old growth. And Cambridge is about 800 and something years old, so they're reasonably good for it. But what is not good for it are the digital systems we're using to design these things. Now, I can barely keep a piece of Python software running for about a year before dependency hell kind of breaks in. And we're trying to build complex petabyte scale computations that will be used by governments to decide policy for decades. And so we have to be more disciplined about how we describe the data and the computation in a way that is self-describing. And there's been lots of papers from this community on self-describing file formats and formal verification, on bootstrapping techniques to start from something simple and build something more complex. And this has to be integrated into these kind of planetary computing systems. Because if I come across a file in 10 years and it's in some weird JSON format with TIFFs attached, I need to know what it means. I need to know where it came from. I need to be able to reconstruct the computation. So there's plenty of scope for thinking through the application of formal specification and formal reasoning in a way that's usable in these kind of geospatial pipelines as well. And again, it's not about drowning the user in data. You want to capture the essence, the heart of the algorithm in order to convey an understanding of what it meant and then progressively build up the complexity so that you can understand the details if you need to, but you should at a glance be able to see what this thing is. And that's what functional programming is really, really good at as well. So this has been a bit of a whirlwind tour through some examples of real conservation efforts that could benefit from computer science, and then a taster on some of the ways that functional programming can help, and then some of the challenges that we're facing moving forward that we have to solve from the research community. And so this whole thing, we're just dubbing programming from the planet. It's just a big catch-all term with one desire, which is to get more people involved in working on matters of biodiversity and climate change. So there's lots and lots of ways to get involved, especially universities are getting heavily involved in setting up interdisciplinary centers where you can hang out with your local ecologists, who are great fun to hang out with in general, because they're full of random facts about whatever they see. But also you can help them to solve their computational problems. And an important part of this is building trust with them as well. It's not just about going in gung-ho and saying that FP can solve their problems. It's about committing to spend your time working with them to build empathy for their problems and then helping them to develop and evolve their code in a way that is maintainable. And that is often one of the stumbling blocks with any kind of research language, is to move it into something that is production quality. And that just takes time, commitment, and energy to kind of pull that off. And the good news is that it's a great opportunity to learn about big areas of science that have large-scale computational problems that often require some mathematical thinking to nail down exactly how to translate them from their high-level description to something that runs really, really fast on a computer. And there are a few things more satisfying in computer science than taking a complex problem, specifying, finding a little trick, and then making it go really, really quickly on whatever CPU or GPU that you have. This is just the dopamine rush that drives me in my programming endeavors. But you can apply this towards social good as well. So we held the first Programming for the Planet workshop at Popple earlier in the year. We've had lots of offers to host more. But really, we don't need a sequential list of these workshops. We need lots of parallel ones popping up, lots of ideas emerging from it, and then occasional get-togethers to figure out how we can exchange ideas and put this together. So my hero, David Attenborough, put this the best. He said, "We are in the final chapter now of the use of the world's resources. This could be a chapter where we end up with a harmonious, steady state view of the planet where we're living in balance with nature and we're satisfying human needs, or it could go in other directions. But the decision is ours to write. So, and I think as computer scientists, we have an enormous amount of power and responsibility with guiding exactly how some of these decisions get made, because of the sheer power of computational processing. And I'm really excited to see what we can do as a community to contribute towards this effort as well. So if any of you want to chat more about this, my coordinates are on Google. I have a very unique name, and I'm always happy to try to figure out how we can have some get-togethers to figure it out. And I look forward to chatting to you after the conference as well. So thank you very much, and I'd be happy to take questions now as well. It's like a planet in front of me, just lots of...
First of all, thank you for your work. I think it's fascinating, and it needs to be done. From the pipeline perspective, your slides kept saying a geo-pipeline, and I appreciate that the geospatial data is very special in the sense that it's spatial. Sorry for the pun. But many of the problems that you described, they are also faced by other scientific fields. So, for example, in bioinformatics, you have many of the same issues, right? So, so is it possible? I mean, it seems like you have something very special. Is it possible that you can also present this type of systems to them, or maybe get something back from them as well?
That's a great question. So the question is, what is really special about processing maps? So I'm one of the maintainers of Docker as well. And so I've seen lots and lots of things wrapped in Docker over the years. And almost every branch of science has got Docker files these days to keep track of their data. Where the first thing that makes, I think, this focus special is a focus on the outcomes. So it's very easy to get distracted when you're coding and saying that, oh, I'm going to drop in this rabbit hole and just kind of keep working the perfect solution here. With these geospatial pipelines, there's problems in every branch. And so it really is pushing it to the end to have a usable outcome. And that's the first focus. The second thing is that there's a real focus when you have lots of divergent data over time, that specifying the data formats is really important. So it's often the case in, say, machine learning, for example, that everything is actually pretty untyped. You've got tensors everywhere, but they don't really have any underlying meaning. In geospatial, there's lots of coordinate transforms. There's hundreds that people use. There's large amounts of data. There's a progress of time, and so you have to somehow spatially, temporally, and computationally make everything align. So that requires a precision in the pipeline, which if you get it wrong, simply gives you the wrong results. And so that's why you demand all these things. And the second thing that's really important, I think, is the security model. There's been very few other areas, apart from perhaps medical data processing, that demands the level of security that we have in geospatial data. Because if you have the world's data in one place, one mistake will actually leak just things that will irrecoverably result in the death of species. And I've had these databases given to me on a USB stick, by people. So this is a very nervous USB stick that is very carefully hidden away. And we need to do better than that. And so it's lovely having a pressure from the use case that demands a high level of security. This is not the case in advertising where you can just get a little bit wrong or you leak a little bit of private data, but there seems to be no repercussions. There's very clear and present danger if we get this wrong. So this demands the discipline and functional programming, I think, in this domain.
Thank you. Is it on? Yeah. So you mentioned a few times in a few different contexts the importance of keeping sensitive data secret so that it doesn't fall into the wrong hands. Given that, for example, sort of digital copying protection hasn't really gotten rid of, say, the Pirate Bay, piracy is still a thing, theft is always going to be a thing. Do you really feel this is a viable goal, or is there perhaps some other mechanism, like, for example, you don't want poachers to know where ivory-producing animals are, but could you go a different route and say, release this data to everybody and introduce, let's say, the concept of poachers and make it profitable to kill those guys that kill the animals?
Yeah, absolutely. So the problem is we only have, that's a good thing. I like the out-of-the-box thinking here. We're going to end up with some kind of Hunger Games scenario. So the problem is we only have one experimental testbed. And so if you get this wrong, and so I've actually run simulations where using reinforcement learning and geospatial data where you can actually play games where you can train agents antagonistically to try to win the conservation war. And it is a war, it is an arms race, right? So it's perfect for reinforcement learning. The problem is that there's no atomic way of rolling this out in an area. So if you think about the actual economics of poaching and preservation, you've got huge areas of natural land. So the Okinawa Delta in Africa or whatever. And there's lots and lots of different political tribes and things there. Then hunters are also illegal more often than not. And so you can't detect them from satellites, so you need on the ground. Then people are bribing other people. And so the actual on the ground realities of conservation are much more dangerous and unpredictable than any kind of clean model that we can come up with. So it's probably not feasible to let half of the world's species die to experiment with different poaching and anti-poaching mechanisms. But is anyone here a birder? Do you like just spotting birds? A few of you, right? Now, when you have rare birds, the data is actually shared, but on only allow-listed kind of groups. So WhatsApp groups that have known good birders, and then they share a sighting, and then they all flock to spot the bird. And so this is what gave me hope that it is possible to build a ground-up peer-to-peer system that says, well, we actually have a community of people who care about the Arctic pika or the African elephant, and then they know who each other are, and so start using DIFC to label each other and just make it easier to manage those groups. And do this per species, so don't try to build a global data structure, do this individually across the 40,000 species, and just keep track of 40,000 values. That seems doable on a modern system. And so the ground-up mechanism is following the existing lines of how people work, and then trying to make the computation support it, whereas the other mechanism where you're trying to change the way the world works, might or might not work, but it probably won't. And if you get it wrong, which is how most science experiments end, you end up with a slaughtered species. So that's why we're not going down the global data structure route, but trying to follow how the world works right now. But I do encourage people to have a go with back-of-the-envelope global simulations, because they're really easy, they're really fun, and they tell you just how complex the world is, because they just go out of control very, very quickly whenever you build them. They're called agent-based models, and there's lots and lots of libraries in most of our functional languages for these kind of things.
Okay, thanks very much. I think perhaps we need to stop, but I'm sure the conversation will carry on.
I've just about to lose my voice, so right, I'm happy to continue more quietly.
So let's say thanks again to Anil.
Thank you all. Thank you.